Energy comes in many forms, and since all forms of energy represent the ability to do work, these different forms of energy can be readily transformed from one to another. Examples of this are all around us. Consider cooking something over a campfire. When the wood is burned, chemical energy stored in the molecules of the wood get converted into electromagnetic energy that radiates away from the fire. Some of this energy is then absorbed by the marshmallow as thermal energy, causing the marshmallow's temperature to rise. The laws of thermodynamics arose from the study of these type of energy transformations. The laws provide a formal description of the way in which energy can move and be transformed. The first law states that energy can neither be created or destroyed, but that it can change from form to form. The law adds that this is true in isolated systems. This is important because the total amount of energy in a system can increase if energy is able to enter from the surrounding environment. When discussing energy, it is important to define the system. To make this clear, scientists often describe thermodynamics in terms of a system and its surrounding environment. When making a distinction between the system and its environment, the first law requires that the total energy of a system and its surrounding environment must remain constant. In our cooking marshmallow example, we can define the system as the marshmallow, making the rest of the diagram, including the fire, the surrounding environment. In this case, the system is gaining energy due to radiant heat entering from the surrounding environment, but the total energy of the system plus the surrounding environment is not changing. If we redefine the system to include the marshmallow and the campfire, the transformation of chemical energy in the wood into heat and radiating to the marshmallow all occur within the system. Of course, only a small amount of the total energy being released by the fire is getting to the marshmallow, meaning the bulk of the energy from the fire leaves the system and enters the surrounding environment as radiant heat. The system is losing heat to the environment, but consistent with the first law of thermodynamics, the total amount of energy within the system and its environment remains constant. The fact that our wood to fire to melting marshmallow system loses most of the chemical energy that was originally in the wood as heat radiating into the surrounding environment captures the meaning of the second law, which states that entropy in an isolated system always increases. As with the first law, this law focuses on isolated systems. Entropy can decrease in a system if energy is allowed to enter from the surrounding environment, but any local decrease in entropy has to result in an increase in entropy somewhere else. The obvious question raised by the second law is, what is entropy? Entropy can be defined in a number of ways. One way is to consider it as a measure of the randomness of a system. This definition is useful in some context, but in the terms of understanding energy flows through systems and the relationships between work, energy, and heat, it is more useful to think of entropy as the reduction of density of energy in a system. The second law then asserts that energy tends to spread out, becoming less densely concentrated over time. Among other things, this helps explain why heat only flows in one direction from regions of higher temperature to regions of lower temperature. The directionality of heat flow is a result of the second law requiring that entropy increase over time, meaning energy density decreases over time. In our wood fire marshmallow system, the second law explains the loss of energy to the environment as radiant heat. The radiant heat is energy becoming less concentrated over time. Thinking about entropy in terms of energy density also captures important ideas about the relationship between work, energy, and heat, and the fact that not all energy in a system is available to do useful work. This points to another useful way to think about entropy, specifically as a thermodynamic property that is the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Again, our cooking marshmallow illustrates this. As the energy stored in the chemical bonds within the wood is converted to radiant heat, most of it spreads out into the surrounding environment as heat, making it unavailable to do useful work. This is not limited to heat from a fire. Consider a bungee jumper standing at the top of a cliff. By climbing to the top of the cliff, this person has converted the effort required to get to the top of the cliff into gravitational energy, potential energy associated with his position above the ground. When he jumps, the gravitational energy is quickly transformed into kinetic energy of motion, along with a small increase in temperature associated with air resistance pushing back on him as he falls. As he reaches the relaxed length of the bungee and it starts to stretch, gravitational and kinetic energy are converted to elastic energy. As the cord stretches, more friction occurs, also adding to the amount of thermal energy. When the bungee is fully stretched, the bulk of the energy still available to do work is stored as elastic energy. This does not represent all of the energy that was present in the system before the jump due to the heat created by air resistance and friction. This heat is energy that is now unavailable to do useful work. As that heat spreads into the environment, it reduces the energy density of the system, all of which is consistent with the second law of thermodynamics. The potential energy stored in the bungee at the bottom of his first bounce gets converted back into kinetic and gravitational energy as he bounces back up. At the top of his first bounce, all of the energy left in the system is back to gravitational energy, but since so much has been lost to heat, he does not bounce back up to where he started. Consistent with the first law of thermodynamics, the sum of the gravitational energy available and the heat generated needs to equal the amount of gravitational energy at the start of the jump. After several more bounces with repeated transformations between kinetic, elastic, and gravitational energy, the bungee jumper stops bouncing. No energy has been destroyed, but it has all been transformed into thermal energy. This thermal energy has dissipated into the environment, making it unavailable to do useful work. In other words, the entropy of the system has increased. In order to jump again, the jumper would need to put work into the system by climbing back to the top of the cliff. The third law of thermodynamics describes absolute zero as the point at which all kinetic molecular motion ceases. This is a theoretical state that is impossible to reach because of the second law's assertion that heat will always flow from higher to lower temperature regions. The closer an area gets to absolute zero, the easier it will be for heat to flow into that region from regions of higher temperature. There is a fourth law. It was added last, but because it helps define the conditions in which other laws operate, it is placed at the beginning of the list and is called the zeroth law. It is a mouthful, but asserts that if there is no difference in temperature between two systems, then heat will not flow between them. Among other things, this is needed in order for us to trust thermometers by allowing us to assume that the temperature reading on a thermometer stops changing when the thermometer reaches the same temperature as the surrounding environment it is measuring.